Markinet, and I'm a professor in mechanical engineering. So last time we talked about how silicon wafers go from being just basic silicon wafers all the way through the manufacturing process, packaging, and ultimately having products. And we saw a presentation from a company that makes the tools that make the patterns that go on the chips. Today we're going to see a presentation from NVIDIA where they're looking at designing the patterns that go on the chips and run all the cool things that we do, from gaming to next generation AI tools. So some of the processes that go into the design are just highlighted here. And the design is not just on the silicon chip itself, but the entire system design. So thinking from the design of what you want to get out of the product, how you're going to make it, and how you're going to package and sell it. So I won't spend too much time on this today because we're going to hear some great information from the speaker. There are some additional outlines here as backup information if you want to learn more about the design process and how things are integrated with chip manufacturing. But with that, we're now going to move on to the lecture. So let me briefly introduce Ronnie Vashishcha, who is responsible for the telecom business strategy and products at NVIDIA. Before NVIDIA, he was very strategically involved in different semiconductor companies, and is, as I said, currently working at NVIDIA as Senior Vice President for Telecom. So I appreciated his fun fact that he shared with us, because as a student and an employee, I've had a lot of long nights myself. So hard work does pay off. So with that, let's welcome Ronnie and look forward to his talk. Thank you.
All right. Thank you very much, everyone. Hopefully you can hear me. So as the introduction said, I'm responsible for the telecom activities at NVIDIA, but today I'm going to be talking a lot more about what really drives a lot of these vertical applications of semiconductors. As you all well know, that semiconductors are at the heart of our daily lives today. And that's probably why you're taking this course, because you want to understand more about what are semiconductors, how are they manufactured, and how are they used. So I'm going to go through a brief introduction of what it is that we do at NVIDIA and how semiconductors play into very, very important roles of the world moving forward. And then at the end of this, my presentation, there's also going to be a very short presentation from somebody at NVIDIA, Kelsey, who's going to tell you a little bit about the types of opportunities offered to undergrads at NVIDIA also. So stay to the end because it's the best part of it. Okay, so as we go through this, firstly, let me tell you that you all should have heard of AI. Who hasn't heard of AI? Okay, so how many of you know what really drives this AI revolution that we're going through today? It's really the hardware and the semiconductors that have enabled us to move so far along already on what is still an early part of this AI journey. So I thought what we'll do as a start is to introduce you to some of the applications that have been enabled by NVIDIA and our partners that we work with in AI. Okay, that should have been a video.
Traveling across the Atlantic to unlock its mysteries. And back in time to understand the origins of the universe. I am a visionary, bringing sharper focus to researchers. And brilliant clarity to surgeons. I am a healer, making treatments as unique as every patient, and giving new life the chance to thrive. I am a guardian, looking out for dangers around us. And in the depths below. I am a helper, enabling healthier, more sustainable crops. Bringing them to market faster and preparing them for the table. I am a creator, building virtual worlds to help robots learn faster and make our connections stronger. I am even an avatar, and you can ask me any question.
Who made this song?
Ava used artificial intelligence to write this song, and it was recorded by the London Symphony Orchestra. I am AI, brought to life by NVIDIA, deep learning, and brilliant minds everywhere.
So that's just some of the examples, of which there are many, of how AI is changing our lives today. What some of you may know is that silicon is driving a lot of this revolution today. And what we do at NVIDIA is we build upon what we think of as a stack. The bottom of the stack is the silicon chips. You heard a little bit earlier today from your professor about how silicon is made and how the ecosystem of silicon enables chip design. On top of the silicon stacks, there's ways of enabling developers to develop the applications that sit on top of those silicon, on top of that hardware layer. So I'm not going to spend too much time today talking about the upper layers, but the upper layers are how we enable the developers and the ecosystem to get access to the chips. I'm going to talk a little bit more today about the chips themselves. What is a GPU? What is a CPU? Hopefully you've all done your pre-read, so this should be just a repeat of what you've already read before the class. But the goal here is the ability to provide a differentiated processing unit. Many of you have heard of CPUs. CPUs, central processing units, consist of a few cores of processing elements that are very good at doing sequential processing tasks, meaning one task followed by another task. GPUs, and I'm going to hit this theme quite a few times during this presentation, GPUs are very good at doing parallel tasks. This is, they contain multiple processing elements, all working at the same time to give and derive an outcome from the data that comes in. So quite different, sequential tasks versus parallel tasks. So GPUs can do thousands of operations a second. And that's why GPUs initially started off in the world of graphics processing engines, because graphics is one of those things that has to be processed in a parallel fashion. Because you view graphics, you can't do this serially. All the polygons need to be rendered at the same time to provide an image on a screen, for instance. So now I'm going to get a little bit deeper into why GPUs have become so important and where CPUs were able to take us as an industry. This graph that you're seeing here is around 42 years of CPU data. What you can see on the top is the explanation of Moore's law. Moore's law was created many years ago to describe how many transistors you can fit within a specific area. And the Moore's law stated that you can fit essentially 2x transistors every 2 years, meaning you can bundle more transistors in the same area, 2x every 2 years. And as you can see on that graph that was produced by, essentially produced by Stanford, you can see that that graph has continued. But where you're seeing a plateauing in something called the performance, the single-threaded performance of a CPU. Unfortunately, the CPU hasn't been able to maintain the same doubling of performance as the number of transistors. There's a lot of reasons for why that has happened. One of the reasons is something called Dennard scaling. Dennard scaling is also depicted on this. Dennard scaling is essentially power density remains constant, which means that the power dissipated by a number of transistors within a certain area remains constant. What has happened, though, is that the power density has increased dramatically because you're unable to reduce the voltage at which the transistors operate at over time. The thing to remember off this graph is that performance has plateaued. And that started happening about 10 years ago. How did we enable all these applications that you saw earlier to still happen, which require tremendous processing power? Well, the GPU, or accelerated compute, came into play about 10 years ago or so. And as you can see from this graph, the green line is the GPU, the parallel processing capabilities that were brought out in the software that enabled that to happen, enabled compute performance to continue to increase. And that's a very important theme that we're going to come on to more as well. CPUs and GPUs exist within a computer system. They're connected. Some tasks are done on a CPU in a serial fashion. Some tasks are offloaded and accelerated on the GPU. They are connected often by a PCI interface, so a standard interface within a compute system. And there's memory within that same compute system. And in this course, semiconductor course, you're going to learn a lot more about memory from some of the other speakers. The memory is what the processing happens, is put into memory, and then you recall information back from that memory. So the compute system itself requires these elements to all work in tandem. So now, let me introduce you to the concept of artificial intelligence. And how artificial intelligence plays into that compute system that I talked about earlier. Artificial intelligence really came about by a concept called deep learning. Same as the brain, our brain, yours and my brain, we learn as we grow up. And we learn by connecting neurons. And we have multiple layers of neurons that learn. That's the same mathematical implementation in a GPU. You can actually use the parallel processing of a GPU to help that GPU learn. And you implement that by layers of neurons. And that's called deep learning. Deep learning pours vast quantities of data through these neural networks, and you're essentially training by back propagating information that comes out of these as you would do with a child, or as you're learning sitting here today. Your neurons are getting connected from what you're learning. We at NVIDIA developed a software programming language called CUDA, the Compute Unified Device Architecture, that made it easy for people to program this deep learning capability. So all the applications that you saw earlier that are programmed on a GPU essentially are programmed through this CUDA interface. So software plays an important role. At the outcome, what are the applications that you've seen some earlier? image and voice analytics, robotics, 2D to 3D transformation, generative AI or large language model training. I'm going to come on to that a little bit later. Speech recognition and translation. All these are learned elements from the data that comes in. Every one of those has been learned by connecting neurons in this stack of deep neural networks. So just to dive into that a little bit more, you can see on this graph how deep learning a neural network works. First, you identify light, dark pixel values. Then you identify images. And by identify, it means that you connect things that are related to each other. It's done in mathematical forms, but things that are related to each other. Some have close relationships, some have distant relationships. You can express those relationships in a matrix. If you slice into one of these AI models, you'll see a number of linear equations that are embedded into each one of these layers. That's a critical thing to remember. This is basically the implementation of math in silicon. GPUs pack thousands of cores, which are essentially all these tiny calculators going through all this linear algebra solutions and connecting those relationships between the outcomes of those layers. And then what we call these streaming multiprocessors, or SMs, that are embedded into the GPU, are highly parallel in nature. They have memory next to them. They say, oh, I remember how those two linear algebra, the output of that linear algebra equation, I'm going to put that in memory. So my next neuron can pull that one back, because now I've learned how these two things connect to each other. It could be words, for instance. How these two words, how these two letters, how these two images, they connect, they're closely connected. So the output of that algebra equation goes into memory, and then you need a lot of memory over time. And that memory interface is what's important. So the arithmetic and other instructions are executed by the SMs, the streaming multiprocessors. Data and code are accessed from the DRAM, what we call layer 2 cache, which exists on the chip. So a GPU system, you'll have, or in a GPU, you'll have hundreds of SMs, you'll have L2 cache, in this case 40 megabytes in our last generation of GPU, and then you'll have this very fast interface that's collecting and connecting all this data, pulling it and pushing it back into the neurons that is coming from the DRAM. The most utilized math function is multiply add. So then we come into the era of generative AI. This is a different era than traditional AI. And how do you implement this in silicon? So you heard earlier about SMs, the streaming multiprocessors. Now we bring in the concept of transformers. A transformer engine basically is able to pick out what's important in a sentence, in a Pantone color scheme. And what I mentioned earlier is you vectorize that in a database, that you can take these close relationships. If I think dog, bark, those are connected. Tree, bark is connected. They may have the same relationship. Dog barks loudly, now you move that relationship more to bias towards one aspect. That's what a transformer engine is able to do. At NVIDIA, we built these transformer engines now into our silicon. That's enabled us to move into the era of generative AI. It's a completely new compute system with a completely new implementation of a neural network that contains transformer engines. So, as I said, the latest GPUs include a transformer engine that can automatically adjust to the optimal precision. What does that mean? Compute is all about precision. If you need very very tight precision, it takes a lot. If you can make your precision lax in your algebra, linear algebra, then you have less compute power required. So we're able to optimize that precision required in a GPU. And that spawned what we think of generative AI. So when you go onto ChatGPT next, or when you go onto any prompt engine next, and you put in these relationships, the method, the silicon that is enabled, you're really going in the data center, you're going to drive, is doing this function. It's connecting these relationships that have been created in a foundational model by training. A lot of data in, you're training constantly these with GPUs, and then you're able to call upon those like a library. And that's how you're able to move from now different modalities, text to video, text to images, animation to, and of course, many different practices have different types of learning. Biology, protein folding. It's a different language, for instance. So let me come on to just now briefly GPU chip manufacturing and design. So you heard earlier about the start of the cycle is silicon wafers, sliced from silicon ingots. Silicon wafers, you have silicon design process with all the functionality that comes on top of that. And you heard just now about some of the functions that are streaming multiprocessors, transformer engines, other math functions that get encoded and designed into the chip. Then you have to make the chip accessible to the outside world. That's actually becoming more and more of a challenge. The heterogeneous packaging, putting different silicon. Here you can see, well, you maybe not see it too well, but you can see different blocks within that chip around the outer edge, those large black blocks. Those are memory chips. Those memory chips are in the same package as the GPU, which is in the middle. The way we design these chips is using design tools from electronic design automation companies like Synopsys or Cadence or others. And we use our own methodology. And before we submit these masks to the wafer fab to get them manufactured, we've already verified the functionality using verification tools. This methodology and flow costs billions of dollars to develop one chip, or to develop one type of chip. And as you can see, on this side, you can see just very high level what the chip would look like from the top down. We use TSMC, which is a foundry based in Taiwan, as our wafer manufacturer. We don't manufacture our own chips. So we're what's called a fabless semiconductor company, that we don't have our own fabs. But we submit that design information to TSMC to have it manufactured. So what I thought I would show you is just a very quick example of that serial versus parallel processing. It's quite a funny example, actually, but this is a good example of a GPU versus a CPU.
All right, I introduced to you Leonardo, and he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1. Let me speed it up. Ladies and gentlemen,
Leonardo
2.0. When we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom up is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU
painting demonstration. And 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ladies and gentlemen, science class is now over. Thank you.
So, CPU and GPU, very different ways of processing data. They both coexist. And of course, GPU, what I've showed you today in terms of what functionality goes into a GPU, what data is processed parallel, is really driving this AI revolution. Thank you very much.
To introduce Kelsey.
Okay.
Kelsey, can you hear me well?
Okay, so as I said earlier, we're going to spend a few minutes also giving you an update, an introduction to some of the undergrad opportunities available at NVIDIA. And so to do that, we have Kelsey Saburi from NVIDIA, who's dialing in to give you that information. Thanks.
Thanks so much, Ronnie. Hi, everyone. I'm so excited to be here. Thanks for letting me join in remotely. So I'd love to talk a little bit about career opportunities at NVIDIA. I am in the campus manager aligned to Purdue, so one of my responsibilities at NVIDIA is to help you all find as many exciting opportunities as possible within our university recruiting program. And if we can go to the next slide. If you would like to check in and stay connected with me and my team, you are absolutely welcome to. I have a QR code here for you if you'd like to scan. But if you're just interested in learning more, you know, what Ronnie was speaking about sparked interest and you'd like to know more and you'd like to see how some of Ronnie's lecture applies to the real world work that we're doing at NVIDIA, you might want to consider engaging with us and checking in. So you can scan this QR code here to get some more information. Next slide, I'll go over some of the exciting opportunities. So we here at NVIDIA in the university recruiting team, we are hiring. We are hiring interns and new college grads. And really, as Ronnie was mentioning, you know, our work between AI and the metaverse is really transforming largest industries and really impacting society. And we would love your help in shaping what comes next. I'll share out the links after the lecture, but I do have some links for you if you'd like to learn more about NVIDIA's university recruiting programs, and then also all of our hiring areas. So really, you know, as Ronnie was speaking, the breadth of opportunity at NVIDIA is really great, and that there are all sorts of different opportunities and areas that you can bring your knowledge and excitement and passion for to help us create what comes next. And if we'd like to move on to the next slide, I'll go over some of the different programs that we have at NVIDIA. So really, your future starts here at NVIDIA. We have several early talent programs, depending on kind of where you are at in your academic career. So we have the NVIDIA Ignite program, which is specifically designed to be sort of a pre-internship program. It's fully immersive for first or second year students. So if your graduation date is sometime after May of 2026, this might be a program that you'd like to consider and learn more. So it's a 12-week pre-internship program, really aimed to give hands-on, real-world exposure to some of the concepts and technical areas that Ronnie was just speaking about. So we have fully immersive. It covers, all of our products, and you get to really engage in the NVIDIA culture and ecosystem that really makes NVIDIA a really unique place to work. We do have 2 cohorts for the Ignite program, so depending on if you're semester-based, which Purdue, yes, so we have a cohort for semester-based students and also a cohort for quarter-based students as well. So there's options there to best fit your academic schedule. And then we also are offering internship opportunities. So we have a robust global intern program that's available year-round. At a minimum, students come to intern at NVIDIA for 12 weeks, and we offer really great benefits. Not only do you get to take part in really meaningful work and make an impact on the next generation of innovation, you'll get to work in real projects and connect with great minds in the industry as you build lifelong connections and networks. We do have programs for students who are pursuing an MBA or PhD, but in general, if your graduation date is after December of this year, 2024, this could be a great program for you. And then lastly, we have new college graduate opportunities. So if you are coming up on graduation or just taking note for the future, we do have full-time opportunities for students who are either have graduated within the past 12 months or will be graduating by next summer. So you'll get to influence areas ranging from high-performance computing and graphics to edge computing, autonomous machines, and so much more. And you really have the opportunity to come in and potentially be a future leader at NVIDIA. And if we can go on to the next slide, I'd love to share some of the areas that we are currently hiring for. So these are the areas here at NVIDIA that we do have opportunities in. And I encourage you to check out some of the links. I have our career site link there, and then I also have sort of a library of these different areas and all of the subsets underneath these domains where you could find opportunities. And one of the exciting things that I hope to be able to help with is to really help you find your perfect fit. Even if you're just exploring some of these topics, figuring out what's of interest to you and seeing that work come to life within the industry here at NVIDIA. So opportunities within hardware, basic, verification, physical design, all of which Ronnie was just speaking of, computer architecture, to software, compilers, systems, graphics, cloud, and into artificial intelligence, deep learning, research, as well as all of the business operations roles that also power NVIDIA on sort of the other side. So I encourage you to take a look at some of the opportunities and browse through the job description packet. It should give you a really good overview of some of the skills that are required for these areas, which really brings me to the next slide. Perfect. For next steps, speaking of skills and what is sort of expected for some of the hiring areas you saw in the previous slide, the first step is really to explore. Go onto the careers portal, see what is out there, get to know the openings that are available that we're currently hiring for. We do have a high volume of roles available, and new roles are coming online continuously. So I do recommend checking back on the careers portal every now and then, and even consider setting up job alerts because there's constantly new opportunities being added. So I do recommend focusing in on the roles where you have some knowledge and experience, also in roles that you're very passionate or areas that you're really interested in. And then for the next step is, I always am asked by students, how do you get noticed? And your resume is kind of your gateway to that. So make sure your resume really aligns to the domains or areas that you're interested in. For technical and engineering opportunities, work on your resume so that you're highlighting your skills, your courses, your past experiences, and class projects, school projects that all help build the qualifications for the position. And then after you have applied online, my team is reviewing resumes every day on an ongoing basis, continuously. And if there is an alignment and a good match, and we have an opportunity that maps back to your interests and passions, then someone from my team will reach out. Another question I'm frequently asked is if there is a specific timeline. There is not a timeline, just because there are so many positions that are coming online continuously. So each position is sort of in a different phase of its recruitment cycle. But if there is a match, then someone from my team will reach out to you directly. And then finally, I just wanted to encourage everyone to stay connected. Really, if you are just starting out and exploring opportunities at NVIDIA, consider following us on LinkedIn. We'd love for you to, follow the NVIDIA blog and stay connected, where we regularly post information about careers, work, and the technology and innovation that we're driving. So again, the QR code, we can put that back up on the screen if we'd like. Consider checking in so that we can stay connected. And I just would love to just say thank you for allowing this time and space, because really, my passion is helping you all, the future, future leaders at NVIDIA, find opportunities. So thank you so much.
All right. Thank you, Kelsey.
So I think we're going to open it up now to Q&A.
Yeah, we're going to start with Q&A now. We have a few minutes for Q&A before class ends. When class ends, if you still have additional questions, you can come down. Let's sit in the front row this time instead of crowding the speaker, and we'll try to take some more additional questions. But to start, I'll use one of the questions that was submitted by students in advance that touches on my own areas of interest. The increasing density of transistors inside your chips and stacking of cores causing increased power dissipation. So what is NVIDIA doing to solve that challenge and keep the operation going to the future?
Yeah, good question. So the laws of physics always apply. So transistors consume power, and as transistors are moving down the nodes, as you quite rightly said, they're actually leakage is also becoming a big factor. It's current leakage. Transistors should be a one-off, one on or off, but they end up having sometimes states in between where current leakage is happening as well. So power is increasing dramatically. We could have GPUs over time that dissipate 1,000 watts of power, just one chip. That's more power density than on the surface of the sun, for instance. And so taking that power off the chip, because you're putting chips in racks that are this tall, or they're going into computers, is a huge challenge. And the way we solve some of those challenges is by adding heat sinks, by increasing the area of the package itself for power dissipation, increasing the airflow of fans that are going over the chip. All of these techniques they in themselves are very fruitful and deep in terms of the research that has to go into these areas. So power density is really driven by the laws of physics. We just have to deal with it.
Great. And then on the sort of the educational and industry side, with the launch of things like NVIDIA's generative AI for drug discovery, is the company investing in these technologies and helping to educate students or partnering with universities to get curriculum going in those directions?
Yeah, so NVIDIA has a program called DLI, Deep Learning Institute. We're constantly evolving DLI for the needs of the needs of the community. More recently, we've just added a lot of generative AI to that capability. And much of DLI, some of DLI is actually also being applied to universities. Some of it's a paid course, but everyone should be able to get access to DLI. So I encourage you to get online and check that out. Of course, also we have twice a year a big conference called GTC. GTC happens in March and in the fall. And there we talk about the newest things that NVIDIA is doing. And so you can actually learn a lot because we're very open and transparent in what we share in GTC as well. So if you get online to that, you register, you'll be able to see the latest and greatest that's coming out from NVIDIA.
Sounds like a great opportunity. Are there any audience questions that people want to ask right now? Yes, you can start.
So you talked about how you had CUDA cores and then you also have tensor cores.
Right.
So I know that a lot of your products sort of augment the two together. So how do they sort of work with each other within your products?
It's a good question. So how do CUDA cores and tensor cores work together? Really, it's an architectural way that we use those, and it's driven by the application. But there's on-chip buses that essentially allow those things to communicate. How many CUDA cores we have, how many SMs or streaming multiprocessors, how many tensor cores, how many transformer engines. It varies by size of GPU. We actually have GPUs that can go on small GPUs for like $20 that go on a robot, right? And then of course we have the much larger ones that I showed you there. So it's somewhat application driven. In terms of the architecture of how do they communicate through on-chip buses.
Another question? Yeah, in the back, if you just shout out, I'll repeat it.
Yeah, so I guess one of my questions about like future of SoCs, like the Tanker line of products, would you consider like small frames for electronics like the Nintendo Switch or something? I know you talked about how like as GPUs are evolving, they're becoming like way more, I guess, like they have to use way more power to like be able to process. I'm just wondering, do you think the future of SoCs is more going to be based on things like DLSS and AI, like enhancing performance, or do you think it's actually going to be finding like more power efficient ways to pack more transistors into the chip?
Yeah, that's a good question. So really the heart of your question is, as we're moving through to SoCs, are there going to be other ways of increasing performance or gaining an outcome without having to go through the power curve increase? I think both things happen. Like DLSS, DLSS is a technique that we use in NVIDIA to enable you to get great graphics. We transmit 1 pixel, we infer the 7 pixels around it through AI, for instance. So that means that you only have to have a transmit 1 pixel to get a great rendering of a game, for instance. That's going to continue to improve and increase. And in the area of telecommunications, SoCs, we're going to try and break Shannon's law by doing that. But yet we can't avoid that power increase. There's always going to be more transistors that are going to be required. Even DLSS requires more transistors to be included to enable DLSS to be implemented. Okay.
All right, probably one more question. Yes.
NVIDIA has grown remarkably quickly over the past few years. What technological advances would you say you could say would attribute directly to that, and what do you think is like the future innovation that you see that will continue that growth?
Yeah. So really, I kind of mentioned it on that first slide where I showed you the stack. The stack, every layer of that stack requires the knowledge of what is on top or below it. Our GPUs, our CPUs, our data processing units, all the silicon hardware is very much dependent upon how that is used. There's very few companies that look at this as a computer stack architecture problem or a systems problem. That's what has enabled us to grow. There'll be other companies that develop GPUs, for sure. We saw CUDA as a way of gaining millions of developers onto the GPU architecture. But viewing this as a complete stack and how those work together is what's enabled us to grow and differentiate.
Great. Well, let's thank the speaker for his talk today.
Thank you.